Okay, so this is an experiment to see if maybe this is going to be better, but I can see that the screen. I will wait for a response. I'm trying a different software to broadcast today. So go ahead and type in if the image is backwards. I can wait. Is the image backwards? Because for me, it looks backwards. And if it's backwards for you guys, then I'm going to have to start this over again. Hey there, Spicy Pepper. Can someone tell me if the image is backwards? Type it into the live chat, please. It's not backwards. Okay, so it's only backwards for me. All right. All right. Well, I will just do my best then. All right. So for your IA by actually just as soon as possible. Okay. If you missed my meme review, what they said is that based on the score that you get on your IA plus my predicted grade, they're going to use that to kind of guess what your IB score would be. And so your IB score is just going to be based on a guess this year. You don't have to take the exam. It's just a guess. All right. So that's a little bit weird, but it is what it is. So I need everybody's IA as soon as possible. All right. So today what we've done so far is we have been learning about atomic physics. So we have the nucleus, and then we have the electron cloud. And what we've been doing is we've just been going inward further and further. So we studied the electron cloud first, and then we studied the nucleus. And now we're going to study what is inside protons and neutrons. So we're going to learn about what are called elementary particles. And an elementary particle is a particle that cannot be broken apart. Okay. So it's just a particle that cannot be broken apart. So all the elementary particles are arranged into something called the Standard Model of particle physics. So this is actually the Standard Model is sort of our best guess at how nature behaves currently. It's called the Standard Model because it's been around for a while, and it's just kind of the model that everyone uses to understand particle physics, okay? So let me tell you about the Standard Model. The Standard Model has 3 types of particles, okay? It has what are called quarks, and quarks are particles that make up protons and neutrons. So protons and neutrons actually elementary. You can break apart a proton, you can break apart a neutron into what are called quarks. Okay. And then there are what are called leptons, which are electron-like particles. Okay. And then there are forces between particles. So, for example, there's a force carrier for the gravitational force. There's a force carrier for the electromagnetic force. So let me tell you about the quarks. The quarks, there are 6 of them. So I'm going to make 6 boxes. Okay. And as we go from left to right along the boxes, it's going to be getting more massive as we go that way. Everything in the top row has a charge of plus 2/3. Everything in the bottom row has a charge of minus 1/3. Okay. So these are the quarks, and there are 6 of them. There's an up quark, which is denoted by U. And there's a down quark, which is denoted by D. There is a charm quark, which is denoted by C. And there is a strange quark that is denoted by S. There is a top quark, denoted by T. And there is a bottom quark, which is denoted by B. Okay, so these are the 6 quarks. By and large, the most common quarks are the up and the down quarks. Okay, because we get more massive as we move to the right, the charm and strange quark, the top and bottom quark, those are more massive than the up and the down quarks. And so consequently, according to E equals mc squared, you need more energy to create these quarks. All right, so these are the quarks. For the leptons, there are 6 leptons. And so again, I will break it up into 6 boxes. And remember, leptons are electron-like particles. So the top row has charge just like an electron. Okay, Q equals -1. And because an electron has a charge of -1. And then the bottom row has charge 0. Okay, so what are the names of the leptons? Well, you have the electron, and then you have what's called the muon, and then you have what's called the tau. So these are all electron-like particles. The muon is like a heavy electron. The tau is like a super heavy electron. Okay. All right. And then each of these leptons has its own what's called a neutrino. So these are the neutrinos. So there's, and it's denoted by the Greek letter nu. There's an electron neutrino. There's a muon neutrino. And there is a tau neutrino. So each electron-like particle has its own neutrino. Now the neutrinos have a mass that is approximately equal to 0. They're extremely light. The particles that constitute matter. So, for example, a proton is actually equal to 3 quarks. It's an up quark, an up quark, and a down quark. All right. And if you think about that, the up quark has what would be the charge of this? Well, the charge would be the charge of the up quark, which is plus 2/3. The charge of the second up quark is also plus 2/3. And the charge of the down quark is minus 1/3. So this gives a total charge of plus 1. Okay. The neutron is up, down, down. And so this has a charge of plus 2/3 minus 1/3 minus 1/3, which is 0. Okay, so the proton and the neutron are made up out of. So now, what I want to talk about is the fundamental forces. Strong nuclear force. Okay. That is the most of the most powerful of the 4 fundamental forces, and it is the force that holds the nucleus together. It's the force that holds the nucleus together. And the strong nuclear force is felt only by the quarks. So only the quarks feel the strong nuclear force. That is the reason why quarks are the ones that are stuck in the nucleus and not the electron. The electron isn't a quark, so it's not stuck in the nucleus. Okay. Now, each of the 4 fundamental forces has a force carrier, or more than one. So there are force carriers. And the force carrier for the strong nuclear force is called a gluon, Gluon. All right. So this is the number 1 most strong of the 4 fundamental forces. The second strongest one is called the electromagnetic force. Basically, it's the electrical force. It's the second strongest. And it is the force that holds electrons to the nucleus. All right. It's the force that holds the electrons to the nucleus. Any particle that has electric charge can experience the electromagnetic force. So it's felt by everything with Q not equal to 0. Okay, so flipping over to the other page here, you could see that the quarks and then the top row of leptons can feel the electromagnetic force. But the neutrinos do not feel the electromagnetic force. The third strongest, ranked number 3, is called the weak nuclear force. Okay, and the weak nuclear force is partially responsible. Basically, you might remember that one of the types of radiation is called beta radiation. And anytime you have beta radiation, the weak nuclear force is responsible for it. So it's responsible for beta radiation. It is felt by quarks, by leptons, quarks and leptons. They all feel the weak nuclear force. Okay. Oh, I have to tell you the force carrier of the electromagnetic force. The force carrier is called the, you already know about the photon. The force carrier for the weak nuclear force is called the W boson. And there's a second one. So the weak force is kind of weird. It has 2 different force carriers. There's the W boson and the Z boson. All right. And lastly, there is the gravitational force, which is the weakest of the 4. Okay. And the gravitational force, you know what the gravitational force is. It's felt by anything with mass. Okay. So basically anything that has mass feels the gravitational force. And its force carrier is called the graviton. So I'm going to redraw my table here. Okay. So we had our table of quarks, up, down, charm, strange, top, bottom. We have our leptons, where you had electron, muon, tau, and you had electron, neutrino, muon, neutrino, and tau neutrino. These had a charge of plus 2/3 and a charge of minus 1/3, a charge of -1, and a charge of 0. And then we also have our force carriers. And how many force carriers are there? Well, there's the gluon, there's the photon, there's the W boson and the Z boson, and then there's the graviton. So that's 5 force carriers. So I'll put a row of 5 here. 1, 2, 3, 4. So there's the gluon, which is denoted by G. Gluons have an electric charge of 0. There is the photon, which is denoted by gamma, which has an electric charge of 0. There is the W boson, which has an electric of +1. W for weak. There is the Z boson. Z stands for 0 because it has an electric charge of 0. And then lastly, there is the graviton, which is also normally denoted by G, which has a charge of 0. Okay? And there is one other particle, which is called the Higgs, H. And Higgs has a charge of 0. So what does the Higgs do? It gives particles mass. So without the Higgs, you have no mass. So this is kind of the list of all the elementary particles. So you can see there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 elementary particles. Also, each particle, I'm going to write this. Each particle has what is called an antiparticle. Okay, and its electric charge. So, for example, an up quark has what's called an anti-up quark, which would have a charge of minus 2/3. Okay. So the antiparticle is denoted with a bar. So the anti-up quark has a bar over the top. That's an anti-up. An anti-down would have a bar over the top. Anything that has a charge of 0. Okay. So at any rate, that's my lesson for today. So if you have an Amazon Prime account, I recommend reading or watching a documentary on the Standard Model. It's called Particle Fever. It's a pretty good one. All right. Hope you guys have a nice day. Please get me your IAs if you haven't already. Bye now.